Hello. We are starting today on the series problems that lead to the proof of the Hazard-Davenport, or should lead to the proof, if I can solve them, of the Hazard-Davenport relation. It's December the 1st. SIR is a set of all reducible polynomials with coefficients in Q, and SD are those of degree D, as it says here. Then we shall write, write this as a product of, or show that it can be written as a product of irreducible monic polynomials whose order divides R. Some time ago I wondered about the number of irreducible polynomials over a prime field, and I looked a little into it today and found out on stackexchange that it's given by this formula. When you see that, you will probably get the idea that it can be proven by adding up the result. And that's actually quite obvious now that I see the formula. If we take like p to 36, it has prime power 2 and 3, or prime 2 and 3, 2 to the 2nd to the 9th. So we make the hierarchy of fields. Q squared is a subfield of Q to the 4th, and Q to the 6th, a subfield of both. And then we have 12 and 18. And then somehow adding the number of polynomials of these. I don't quite know the details because I was thinking in a more complicated way, but I think it would be a relatively simple exercise to prove this formula once you've seen the result and once you get the idea that if you call this Si of n, then we have to add them for all d's dividing n, and then get some known number, which should be q to nth, and then there's a factor n I don't know about. So I think it's pretty obvious to do it, but I can't just see how to do the details, but I'm sure you will be able to do it. All right. Now, I think the theorem is quite obvious if it's a prime power and not if it's if the base q is a prime, using these guys, because we take those, or let the choose 1a and let the Galois group work on it, and if it has like only 2 or 1 conjugate, then those 2 you multiply the polynomial out and get an irreducible polynomial with coefficients in Fp itself. So I believe it's quite obvious when Q is a prime itself. And we use no more than this, so I believe all we have to do is to show that these 2 well-known formulas or theorems, propositions, hold for a prime power instead of a prime. And I just have to go through the details, though it seems obvious to me, but we'll just do it. First of all, the splitting field of f q to nth And we say that Q is, they don't say, P to rth. So that's the splitting field. And by this, the proposition A, it's given by P to n rth minus x. And P to rth is Q, so that's just Q to nth minus x, as it should be. And that's with coefficient O. Then the coefficients must be in FQ. But it's a monic polynomial, and the coefficient -1 lies in FQ as well. Need to do all the details. Next, this guy. Now it should be Q. It's the same as P to nr, P to mr, and by the proposition, that's equivalent to now what's this? Oh, it's mr and nr. So mr dividing nr, and that's equivalent to m dividing n. And then the index, you can probably see where it's going. This is an R, not an M, so it's N divided by M. So this guy turned out very easy, and the first time didn't take much longer.